So they say carbon monoxide and hydrogen react as follows, and it's a reversible reaction to form methane and water. It's carbon monoxide, which is a gas, and what? Hydrogen. Hydrogen, 3H2. Thank you for helping me. It's a reversible reaction and it forms methane, CH4, also called earth gas. Am I right? And after the methane, what do they give us? Water. H2O, also in a gaseous form. Now you see why it's important that they give us the state of the reactants. Okay. Now they say when 1 mole of carbon monoxide reacts with 3 moles of hydrogen in a 10 cubic decimeter container at 927 degrees, the reaction reaches equilibrium with 0.4 moles of water in the equilibrium mixture. Calculate the molar composition of the equilibrium mixture and Kc. So the mole ratio is needed. 1 mole to 3 moles gives us 1 mole to 1 mole. Okay. They don't say anything about the forward reaction being exo or endothermic, but they tell us that the temperature is 927 degrees Celsius. So they tell us what the temperature is. The temperature is 927 degrees Celsius. They also tell us that at equilibrium we have, at equilibrium we have 0.4 mole per cubic decimeter. So what did we start off with here? What do they say we're starting off with? What are they putting into the container?
1 mole of CO2.
1 mole. So this is given, and 3 moles. They are giving us this, and what could be confusing is that these moles that they give us corresponds to the moles in the balanced equation. Okay, that can be a confusing thing. Let's see. And they told us that the volume of this container is 10. Volume is 10 cubic decimeters. Sorry, I'm going off the screen. Okay. How much would we have at the start of the methane? How much would we have? They put 1 mole of carbon monoxide and 3 moles of hydrogen in.
We have 1 mole.
Aye. No. 0. You start with nothing there.
Oh, wait.
And how much water will we have?
Nothing.
Nothing. This is what we have at the start. Are you with me? So they're telling you that you're starting off with 1 and 3 moles. When you put these gases into your container, your 10 cubic decimeter container, there is no methane and no water vapor in there. Yeah. Then something happens. Something will be used and something will be formed. Okay. Something's going to reach the equilibrium. The reaction is going to reach equilibrium. Okay. I don't know yet. I have to continue reading. So they say the reaction reaches equilibrium with 0.4 moles of water in the equilibrium mixture. So at equilibrium, for it to reach equilibrium, I know that the temperature must be kept constant. Okay. At equilibrium, they find that there is 0.4 moles of the water. So how much water was formed? 0.4. So 0.4 moles of water was formed. So in my, so you see, I write my mole ratio, then I write what we started off with, then I skip a line, then I write what I've got at equilibrium. So they told me I've got 0.4 moles of water at equilibrium. So how much water was formed? 0.4 moles. So from here I work one step back. From what was given here, I go one step back. Okay. Now, how much methane would have been formed if 0.4 moles of water vapor was formed? You see, so I'll work one mole, I will work one step back again. So from the 0.4 given here at equilibrium, I know that 0.4 moles of water vapor was formed, and they formed in the ratio 1 to 1, the methane and the water. So I know 0.4 moles of methane would have been formed. So how much methane would I have at equilibrium? 0.4. So I go one step down, because 0 plus 0.4 is 0.4 mole. Okay. Now we need to know how much hydrogen was used if 0.4 moles of methane was formed.
1.3.
What must I do to calculate that amount?
Would you multiply this in the ratio?
Well, what do I do to take a 1 to a 3?
Times by 3.
So the same thing I must do here, times by 3. So how much hydrogen would have been used?
It would have been 1.2 moles.
1.2 moles. So 1.2 moles of the hydrogen was used. Originally you started off with 3 moles, but obviously you won't end off with 3 moles. 1.2 moles were used. Now I have the habit, because I say it's used, I'm going to subtract it from what they're giving us. Okay? So here we go. What will be at equilibrium? 1,8 moles. So from, you see the red arrow, I'm following the red arrow from what is given. Okay?
Say 3
You-
minus 1.2.
You say 3 minus 1.2, yes. Okay? Yes?
So this one we started with 3 moles and then now the 1.2 is used.
Yes, to form the methane and the water. Okay. How much of the carbon monoxide would be used? So I can use this ratio, 1 methane will be formed by 1 carbon monoxide. So how much carbon monoxide would be used? 0.4. And I'm going to subtract that amount from the starting amount. So what will be at equilibrium? Like that. Okay. So the question asked us, calculate the molar composition of the equilibrium mixture. So do we have the molar composition of the equilibrium mixture? Yes, we do. At equilibrium, we'll have 0.6 carbon monoxide in that container. Remember, it's a sealed off container at constant temperature. and we'll have 1.8 moles of hydrogen, we'll have 0.4 moles of methane, and 0.4 moles of water. Everything, we've checked it, everything is gaseous, so it is a homogeneous reaction mixture. Now to get Kc, next thing that we need to do is to get Kc. Now Kc is, I need equilibrium concentrations for Kc. And that is where we're going to use the 10 cubic decimeters. We're going to use the 10 cubic decimeter to calculate the concentrations. So my equation for concentration is mole divided by volume. So here we have 0.6 divided by 10, which is 0.06 mole per cubic decimeter. And this one divided by 10 is 0.18 mole per cubic decimeter. Sorry, my space is running out. And this one will be 0.04 moles per cubic decimeter. And this one is 0.04 mole per cubic decimeter. You with me? Okay. Number 3 on page 186. Okay. Now, Kc. Now, some people just want to say brackets product divided by brackets reactants. It's not working that way. You actually have to write the equation down for the specific situation. So we start off with the product, so it's concentration of CH4 times the concentration of H2O. Remember, if the H2O would have been liquid, you don't put it in. Divided by the concentration of carbon monoxide times the concentration of hydrogen to the power 3. Okay? So there it would be 0.4. Can I say, no, 0.04. Can I say 0.04 squared just to?
No.
Yes. There's two
What
0.04s. So it's squared.
And it's fine, we don't have to fight about it. And then this is 0.06 times 0.18 to the power 3. Am I right? Okay. What is the value of this? I'm a bit slower on my Casio than on my Sharp. 4.57. So what is this value telling us?
Equilibrium lies on the right.
Equilibrium lies to the right, yes.
So not if it's lower than.
If it's small or smaller than 1, like 0.0 something, or 0.1, 1 would mean that the concentrations of the products, I'm saying it wrong now, the product of the concentrations of the products equals the product of the concentrations of the reactants. Then your your equilibrium is not lying to the left or to the right.
It's perfectly like in the middle. Like
Yeah.
So it's not necessarily, it doesn't have to be a negative number for it to lie on the left.
No, it won't be a negative number. It must be a number smaller than 1.
So we can't ever get negatives.
Now, if you get negatives, how do you measure concentrations and moles in negatives? I'm putting these negatives there because I'm reminding myself that those amounts are used. Those amounts are formed. So technically you add them to get your equilibrium constant, equilibrium concentration. Say we started with 1 mole there. We might have had 1 mole plus 0.4 moles. So 1.4 moles. We could have had that situation. But in this question we didn't. Right. Are you happy?
Yes, ma'am.
Must I wait a moment?
Yes, please.